We have Professor Sir Tejinder Virdee speaking to us. In fact, he's speaking from CERN in Switzerland, and he's really going to tell us about the future of that great organization, I suppose, what lies beyond the Higgs boson. Can I just remind you that the way to ask questions effectively is to use the chat, and we'll be keeping an eye on that, and we'll ask questions of Jim at the end. And otherwise, very good to see you all. And I would like then to introduce Jim and give you the floor. So, Jim, welcome.
Thank you. You need to unmute me?
We can hear you.
Oh, you can? Okay. Oh,
Yeah.
It appears muted on my screen, but that's because I'm actually sharing. Okay, great. Thanks. Thanks for the opportunity to talk to you guys. Normally, you guys have come over and I've shown you around the hardware, so this is going to be a bit more remote. Now, I'm going to tell you something about the Higgs boson itself, and then raise some questions as to what lies ahead. In fact, the Higgs boson itself actually generates more questions than answers, in fact. So as you know, at the LHC, or the Large Hadron Collider, we go to very high energies, which allow us to probe nature moments after the Big Bang. And so this allows us to actually ask questions about the origin, evolution, and the composition of our universe. And some of these questions go to the heart of our existence, in a sense. And things like, what is the origin of mass? What constitutes dark matter? How many dimensions of space and time do we live in? And why is the universe composed of matter and not antimatter as well? And so the answers to these questions have the ability to alter our perception of nature and how it operates at the fundamental level. Now, the discovery in July 2012 of the Higgs boson completes the particle content of the standard model. It doesn't complete the standard model because there are many questions which are still open. But the standard model of particle physics is a theory. In fact, it's a quantum theory of three interactions. And it describes our visible universe, and I use the word visible wisely, in quite great detail. And so I'm going to give you some idea of that and then go and ask further questions. And so now let me start. So the audience is probably mixed, so bear with me if I get into some difficult areas, but I'll try to keep it as simple as I can. So particle physics is a modern name for a centuries-old effort to understand the laws of nature. So that really is what it is. And there are only two questions we're trying to answer. What are the elementary constituents that make up our universe? And what are the forces that control their behavior? And experimentally, what it means is that we have to make particles interact at higher and higher energies and study the products and properties of the particles that come out of the interaction and measure their energy and direction and the type of these new particles that are produced as accurately as possible, and use computing systems to reconstruct what happened. So the mission statement is rather simple, but of course it takes huge amounts of information and complicated instruments to get there. So I think you're all very familiar with the structure of matter. So you have molecules and atoms have electrons and nuclei have protons and neutrons and protons have constituents called quarks, and that's the limit that we've reached. And we've actually probed at the LHC structures which would be 100,000th of the size of the protons, for example, and we find no other structures as such. So for the moment, quarks are the most fundamental objects we've discovered. I'm going to be using quantities called electron volts. I'm going to be using mega electron volts, giga electron volts, and tera electron volts. And to give you an idea, and the electron volt is a convertible currency in the sense that we can equate it to temperature, we can equate it to mass, and we can equate it to time. So what's happened here? Okay, so just to give you an idea, if you wanted to take out an electron from an atom, let's say hydrogen atom, you need 10 times the 1.5 volt batteries. If you want to take out a proton from a nucleus or a neutron from a nucleus, you need 10 million of these, 10 MeV. And at the LHC, we essentially have energies which is equivalent to 5 trillion batteries. And so that's the structure in terms of matter that we are familiar with, the U quarks and D quarks and electrons and neutrinos. Now, in terms of the interactions, we have 4 interactions, which are the basic interactions: the strong interaction, electromagnetic, weak, and gravitational. You're very familiar with the gravitational one, and also the electromagnetic one, which determines what happens with bar magnets, for example. The weak interaction is the one that generates energy in the sun, and the strong interaction is what holds the quarks glued into the protons and neutrons. And so those mediators are called gluons. Now, in interactions, you have to exchange energy. And it's in very much what I'm doing now. I'm exchanging essentially information by the spoken word or visuals, but particles interact by exchanging energy. You need to have some sort of exchange, otherwise you don't feel the interaction. And the exchanges come in quanta, in packets of energy. And so the different types of interactions are mediated by different types of particles. For example, the electromagnetic by the photon, and the weak interaction by the W and Z bosons, and so on. So these are the force particles. Now, all of the known forces in our visible world can be attributed to these 4 interactions. And we have quantum theories of strong electromagnetic and weak interactions, but not yet of gravity. So that's one of the big open problems we face in physics. Now, particle accelerators are used actually to determine what the structure and what types of particles exist in the universe. And we accelerate particles to very high energies and collide them. And why do we need very high energies? Energy is related to temperature by the Boltzmann relation. Is directly proportional by the Boltzmann constant. And so if you go to very high energies, you're effectively going to very high temperatures. And we know that the conjecture is that the universe was created in a hot Big Bang. So higher temperatures means going back into the origins of our universe. So these are essentially very powerful telescopes. The other one you're familiar with is equal to mc squared. So if you want to make a particle like the Higgs boson, which is quite heavy, that you need a lot of energy. So that's E equals mc squared from Einstein. Another one which comes from de Broglie, beginning of the last century, was that energy is inversely proportional to size that you're probing. So if you have a very powerful, very high energy probe, then you can look at very small distances. So the accelerators also act as powerful microscopes as such. So they're not only powerful telescopes, they're also powerful microscopes at the same time. And so this allows us to observe phenomena and particles normally no longer observable in our universe, in our everyday experience, but all in a controlled way. Now, this is one interaction at the LHC, one of the first ones, in fact, in 2010. And what you see is a proton coming in from the top left hand and another one coming from bottom right and interacting in the middle of the detector. The particles are color coded. There are 4 layers in the detector, and each one is a different color. And so the first layer is singing in yellow, the second one in red, third one in blue, and the fourth one, there's not much activity, which is in green. So this actually shows you the production of new particles from the protons interacting. And what you see is the collimated bunches of particles. And these are indicative of the quarks and the gluons, which are inside the proton, which actually are manifesting themselves inside our detectors, that collimated bunches of particles. One other thing you can do is to take 2 particles, for example, take the one here and one here, which are oppositely charged because they're bending oppositely, and take their energies in directions and create a quantity called the invariant mass. And the invariant mass is essentially the quantity from which these 2 particles might have arisen. Normally, they're randomly distributed, so you should see no particular preponderance in one mass compared to another. If there's a real particle, then you'll see a lot more particles with a given invariant mass than in the surrounding, in the neighborhood as such. And that's indicative of a particle. So we do all of this, and this is a plot that was produced 1 month after we started taking data. And this actually traces back the history of particle physics. These particles were found in 1960s before I started my PhD. This was found in 1974, and that was when I started my PhD, and these came later, as you see, higher energies. And these are the anti-charm quark bound states, and these are anti-bottom bound states. So these are new types of quarks, and these are the standard quarks that we are made of. And these were made by accelerators themselves. And this is the Z boson, which was discovered in 1983. So this maps somehow the history of particle physics, but also tells you what a particle looks like for us. And we also can check how good our apparatus is by trying to resolve these peaks. And this peak has been resolved this way. And the width of these things tells us something about the quality of our instruments. And we want the peaks to be as narrow as possible so they stick out like sore thumbs and easy to then see. So that's one of the aims in a sense. Now, let me then summarize where we stand in terms of the standard model. So it has taken a long time. The Higgs boson, for example, was postulated in 1964. And as I mentioned, the last particle that was found in top quark was in the 1990s as such. So we have 3 generations of fermion particles, spin half matter particles, and they interact by forces mediated by the Z and W bosons of weak interaction, the gluon for the strong and the photon for the electromagnetic, for example. Gravity is missing here. And this is described by quantum theories of 3 of the 4 interactions. Although these are only 4 lines, when you develop this thing, it's about 3 or 4 pages of formula which actually describe all the interactions. But grossly speaking, the first line actually deals with the force fields as such. So these are the force fields that describe the forces. The second line here is actually describing the matter particles, which is this set here. And we have 3 generations. We don't know why we have 3 generations, although some clues are there. We only need the first generation for what we see in everyday life. And the third line is actually the interaction, because these are interacting theories, so particles that do interact. And so you need to actually take account of that. And that third line actually describes the interactions that can occur. Of course, there are many, many types of interactions that can occur, and each interaction has its own line. And this is just a gross one. And the fourth line is actually the Higgs boson itself, which is the keystone of the standard model. Without that, it doesn't stand scrutiny. It doesn't stand on its own. So either we had to find the Higgs boson or something that substituted for it. And eventually we found the Higgs boson as such. So now, just before we move on to where we stand, there were quite a few questions that we knew about right before we started taking data. The first one is Newton's unfinished business, in a sense. What is the origin of mass? He says something about the mass itself, F equals ma, but it doesn't tell us how mass arises. And mass is rather important in the sense that without particles with mass, there would be no structure in the universe. I wouldn't be here talking to you because we wouldn't be able to form atoms. Everything would be moving at the speed of light and nothing would bind together. And then there are other things we knew about, this little embarrassments, which is rather a big embarrassment because it constitutes 96% of the universe, which is dark matter and dark energy. What are these? And nature's favoritism, which I mentioned, where has the antimatter disappeared? And so let me just give you some feeling for the Higgs boson now. Now, to Newton, it was F equals ma. So that means that the force that you apply to get an object to a given acceleration depends on its mass. The force is larger the mass. And Einstein said E equals mc squared, but he also told us that mass is actually something quite fundamentally, that it curves space-time. But they didn't tell us how the mass arises. And so the simplest way to look at it is that in fact, there is a field which is pervading our entire universe, and particles which start off massless interact with this field and acquire mass, and the strength of the interaction determines the mass of the objects that are interacting. And the field is a quantum field, so it must have a quantum associated with it. And that quantum is the Higgs boson. So if you find the Higgs boson, you establish that this field exists. And it's a very strange field because it's an omnipotent field and omnipresent, and you can't switch it off. In electromagnetism, you can take the test charge to infinity and you feel zero force, but this one you can't switch it off as such. So this is a very peculiar object, very peculiar particle, and very peculiar field. And that raises many, many questions. So let me just move forward. So this is the detector itself, the CMS detector. It's one of the big pieces that was transported in February 2007. And this, just showing this to give you the scale of the things that we had to build to discover the Higgs boson. And you can see the people standing there. It gives you an idea of the size. And so there's a lot of engineering involved. So these experiments cannot actually function without sophisticated engineering, whether it's electronics, computing, mechanical, electrical, civil, whatever. This is 100 meters underground in the outskirts of Geneva. So this was the detector now ready to give you an idea. This gives the scale. It's a 5-story high object, and this is this person standing there. And so the beams will come in here from an interact in the middle here. There's another set of beams coming from the other side. On either side of this is the LHC tunnel. So this is now the detector, a cut of the detector. You can see the sophisticated engineering. This is a photograph, in fact, a very high resolution photograph. There are 4 layers. There's the first layer is here, the second there, the third one is this one here. And there's a magnet which allows us to measure the momentum of charged particles, and the muon system, which actually as a return yoke of the magnetic field, and so on. So it's rather sophisticated engineering and detector technology, which had to be pushed to the limits or new ones invented. So let me now actually give you a little bit of an idea of actually Imperial and the Standard Model itself. I think the Imperial College group, the theory group, especially in the 60s, was where most of the action actually took place in our field. So I highlight in red the people concerned at the time. And Tom Kibble was one of the 6 people who postulated the existence of this field. But these papers, which were published in 1964, attracted very little attention, and the boson attracted even less. Nobody was paying any attention to this. To our cost to a certain extent, and experimentalists were not looking at what our theory friends and the next corridor were doing. We should have been actually looking at what they were doing. And in 1967, there's a key paper written by Tom Kibble, this time on his own, which applied these ideas of what we call spontaneous symmetry breaking, which actually says particles without mass through this symmetry breaking gives mass to the particles, because there's no simpler structure than a massless particle as such. So that's where the full symmetry is kept. Every particle that should exist is massless, but of course that doesn't describe the natural world that we live in. And so Tom Kibble was the person who actually put forward the hypothesis that linked these things to the real world. And then that gave the clue to Weinberg to set up the electroweak unification, and independent by Abdul Salam, who was also the professor at Imperial College. Now, electroweak unification is actually, what it says is that the mathematical structure of electromagnetism, which is the force that determines how bar magnets operate, let's say, and the weak interaction, which is what's happening in the sun with the fusion reactions, have the same maths and they have the same structure. And they look different in our world because we are at a low energy. If you got to very, very high energies or very high temperatures, you wouldn't be able to tell the difference between the two of them. And indeed, this is what we find by doing our experiments. And the fact that we found W and Z bosons is very suggestive that this indeed is the case. So the unification has a long history, in a sense. Newton started with terrestrial and celestial gravity unification, and then Maxwell with electricity and magnetism. So there's a big trend, arc of progress, if you like, in unification. So it's natural that we physicists think that there is an overarching unified theory which should include gravity at some point. Now, the key prediction was this W and Z bosons by Salam and Weinberg, and these were found in 1983. At that point, and I was on that experiment as well, at that point, many of us then started focusing on the particle that was the most important missing piece left, which was the Higgs boson. It's one of the first pieces to be postulated in '64 and the last to be found as such. And so this actually is an interesting photograph because this is the day after I gave a seminar after the discovery of the Higgs boson. And after the seminar, I sat with Tom Kibble and I was explaining some points to him. But I like this photo because it's also the photograph of Abdul Salam in the background looking, sort of looking towards us. And so in that sense, the work of Tom Kibble and Abdul Salam actually did set the framework for big pieces of the standard model. Abdul Salam was also quite key in another discipline, parity violation. He missed the Nobel Prize there by a few weeks. So these are what the Higgs boson candidate would look in our detector. So it's similar to the one I showed you. In this case, these are two photons, and the height of these things tells you the energy. And of course, you can work out the direction. So you can make the invariant mass of this thing and then plot it. And if you see in the plot a peak, then you know that you found a new particle. And similarly, the Higgs boson can appear in different guises. And on the right-hand side, it's a guise where there's 2 electrons and 2 muons, particles of the standard model. And so this actually then shows you the discovery as such. So they're not very impressive bumps as such, but they appear in the same place in different ways that we look for the Higgs boson and 2 different experiments. And that actually was the discovery of the Higgs boson. So that's what a Higgs boson or a particle looks like. Now, one of the properties of the Higgs boson is that it couples to provide mass to different types of particles. And if you then scale the mass in a particular manner, then all of these particles and their couplings should sit on a straight line, which is shown here. So this is a particle which is about 170 times the mass of the proton. And on this side, there's a particle which is 1/10 of the mass of the proton. And you can see the huge range of masses. And in fact, one of the problems we face is how does this range of masses arise? We know the Higgs mechanism gives the masses, but why are they so different? And so we don't know the answer to that. The precision of the measurements is at the level of about 10%, which is shown here. But these theories that we have beyond the standard model have now, some of them only show deviations from this line by 1%. So we're not there yet. So that means that enormous amounts of data are still to be taken to actually start saying that this is definitely a standard model Higgs boson, because the predictions are very, very precise. So now let's go and look into the future. So what are the problems? Now, there's a lot of observational evidence that there's something not right with the standard model because there are things it can't explain. So one of the first things is that neutrinos in the last 5 to 10 years, we found that they have very small mass. And since they have a small mass, they can oscillate from one type to another type. And these have been observed, and these are oscillations. So there's a quantum phenomenon. Then there's also another problem, which is a problem inherent in the Higgs boson. If it's a fundamental spin zero, special type of particle, then it should get quantum corrections, which every particle does have. But these quantum corrections, because of the peculiarity of the Higgs boson, take on very high values. It has a mass of 100 GeV, that's where we found it. But it can get corrections which are 15 orders of magnitude, 13 orders of magnitude larger. So you can't have 100 GeV plus or minus 10 to the power 13. So that's something like more. So it's something like 10,000 billion times its mass. So there's something wrong. So something is protecting the mass. And so there must be a bodyguard of particles. And this was thought to be supersymmetry. And when we started taking data, that's where I would have put my bet as being finding the new particles first, but we haven't found them. So nature is a bit more complicated than we think. There's also dark matter. And we can see this thing by actually looking at the rotation curves, and the data are shown as points. And if there was no dark matter, you should see the dotted line, which clearly is not the case. And so that is indicative that there is more mass in our galaxies than we see. So this is why we call it dark matter. So I use the word visible universe to describe the stuff that is, that the 5% of the stuff that we can actually observe. And then there is also matter-antimatter asymmetry, and something else which is dark energy, which comes in two forms. The evidence comes in two forms from the cosmic microwave background radiation. And this is a plot summarizing all the data. And supernova, looking at the distances and the redshifts and the standard candle, which the supernova is, seems to be the velocity of recession is increasing as you go further out, suggesting there's something that's pushing things out, or space is pushing things outwards faster than what gravity would have done, because gravity only pulls. So people were expecting the velocities to be actually decreasing rather than increasing. So that's indicative of something. And I'll connect that to the Higgs boson itself in a few minutes. So let's look at the particle physics issues, which are actually summarizing also some of the cosmological issues. And so this is something which may be a bit technical, but I just wanted to give you a feeling of where the problems actually sit. And so many of the issues actually come from the Higgs boson sector, the particle that we've found. And we don't actually understand the nature of this particle and why its mass is so low, and what role it plays in actually in the early universe when the electroweak transition took place, or phase transition took place. So that means when the W and Z bosons, starting as massless objects, acquired mass. So when electromagnetism and weak interaction separated as two distinct forces that we see today, which were unified at the time. So this is a very important epoch in our universe when a phase transition takes place. And we need to understand the Higgs potential to understand what exactly was happening, let's say a factor 10 higher in temperature compared to the phase transition temperature. And that means higher energy than we have at the LHC as such, to really understand what was going on in the universe. And the other thing that seems to be the case is that we seem to be sitting in a metastable universe. If you look at the top mass and the Higgs mass, it tells us that we are in a metastable place in the universe, meaning that the universe can actually, if the Higgs potential deviates at a very high temperature, then the Mexican hat actually droops, and you create a quantum barrier, and our universe would tunnel through this quantum barrier. Fortunately for us, it's orders of magnitude larger than the lifetime of the universe so far, so it's not likely to happen anytime soon. But it does raise a conundrum as such. And then we would like to embed the standard model into a broader framework, the unification of forces, as I mentioned, and also attempts to give particle physics explanations of cosmological properties. This may be the case or may not be the case. We don't know the answer to this. So being particle physicists, we think there might be a particle physics or particle explanation to dark matter and dark energy. And in fact, the Higgs, a collection of Higgs bosons, being very peculiar particles, spin half particles, at low temperatures act as if they exert negative pressure, and exactly the sort of things that would generate the acceleration of the expansion of the universe, which we currently are observing, or inflation that might have occurred in the early universe. So understanding the Higgs boson and this special field may have an application in other parts of physics as well. So this could be a super Higgs field which actually drove inflation in the early moments of the universe, which makes it look very uniform every which way we look. And the cosmic microwave radiation is the same, 1 part in 10 to the 5, and so on. So there are obviously new theories which were put forward: supersymmetry, superstring theory, extra dimensions, but we have seen no evidence for any of these things, although they're very appealing in their own right. But again, nature, we experimentalists tend to just accept what nature is telling us, not what is elegant necessarily. So let me come to the point, the second part, let's say, the what are we thinking of doing? So I've given you an impression that we would like to take a lot more, record a lot more Higgs boson, try to understand what we have actually found, and still look for new physics, meaning with higher statistics, and also study things which we know quite precisely to even more precise detail, see if there are any deviations. And in 2013, particle physics goes through a bottom-up strategy every 5 or 6 years. And 2013, it considered the full exploitation of the LHC at CERN to be the highest priority, meaning that you record roughly 10 times more data than the original LHC was. And that's what we call the high luminosity LHC, LHC. So the idea is to increase the amount of data to 3,000 inverse femtometer. I won't belabor what the femtobarn is, but today we stand at 130, so we want to get to 3,000. So a factor about 20 to 30 more. And this allows us to do the physics that I just mentioned. Now, so that program is approved, and in fact, that's my current preoccupation, is to actually change some of the detectors, because the radiation levels are correspondingly 10 times higher, and some of the detectors that we had in the original detector will not function with 10 times more radiation. They will just die. So we need to develop new detectors, and that's one of the things that I'm doing. Interestingly enough, these are very challenging things, because you've got to make things 10 times more radiation hard, and the numbers of particles coming out increase by a factor of 10 per second. So the detectors have to be much more powerful than the original ones, but we are, I think we'll be able to do them in the timeline that we have. So the high luminosity LHC is supposed to start working, operating in 2027. So there's still about 5-6 years to go, and we're constructing the new detectors for that at the moment. And this will continue for 10 more years, up to about 2037. So what looks beyond that? Now, so to answer some of the questions that I listed earlier, one does need to actually not only get a very large but clean sample of the Higgs bosons to really study it very precisely. And whenever we find a particle like the W and Z bosons we found in PP, proton-antiproton collisions in the 80s, we then constructed the electron-positron collider, the LEP collider, to study the Z boson in great detail. And so similarly, one would like to actually produce a very large number of Higgs bosons in very clean conditions and study and try to address some of the questions I was raising earlier. But one of the questions which actually is a deep question is to try to understand what the shape of the Higgs potential is. And the potentials play a very important role in physics, because it determines all the structure of the forces. For example, the Coulomb potential tells us how atomic physics works, for example, to a certain extent. And so knowing the potentials is quite important. And the Higgs boson is peculiar that it interacts with itself. Most particles cannot interact with each other unless they do it through a mediating particle. The Higgs can interact directly with itself, and that leads to a complication in its potential. And we would like to understand this interaction, but that requires a factor 10 times higher energy than we possibly have at the moment. So the thought is that perhaps a collider of about 100 TeV, which is about 10 times the energy of the LHC, in the second half of this century would be something that would be actually something that would allow us to address some of the questions we're raising. Now, clearly one has to be aware of the sociological and the financial issues involved. These are expensive instruments, and so these are not given as such. And so this is something which is something which we have to justify, and obviously it'd be quite difficult to build. And the background actually picture is the picture of the Geneva Basin. And just the next slide, I'll tell you what it means. So the LHC is this thing, red line here, which is sitting quite snugly in the basin. And that's a lake there, you can just about make, and that's a fountain just sticking out there, the Geneva fountain. Oops. So that's the Geneva fountain, and that's the Mont Blanc at the back there. And this is the mountain range called the Salève. So if you had to make a 100 TeV collider, it will be a 100-kilometer tunnel, which will go behind these mountains through the lake here, underneath the lake, obviously, about 400 meters underground, and go on the other side. So it's a major, would be a major civil engineering undertaking as well. So that's actually what the strategy group actually was indicating. Europe, together with its international partners, should investigate the technical and financial feasibility of a future hadron collider at CERN with a center of mass energy of at least 100 TeV, with an electron-positron Higgs and electroweak factory as a possible first stage, which is this step here. So you could do both of them with this tunnel, but you need to actually get the tunnel first before you can put any machinery inside. So let me now summarize. So on the left-hand side, we have the standard model particle physics, which is quite, describes the visible universe, which is this atoms line here, the 4.6%. And we have no clue as to what exactly dark matter is, and even less of a clue what dark energy is. Although, as I mentioned earlier, there might be some connections to the Higgs field as such, the scalar field, which is the Higgs field. So summarizing, so I think over the last 50 years, I haven't really given much evidence of that, although I've indicated that some of the things started in the early 60s. We have constructed the standard model, both from theoretical contributions and the experimental ones. And it is a towering intellectual achievement of humankind. I think this is the most precise theory we've ever constructed, and it's a quantum theory. It allows us to calculate things to great precision. But nevertheless, we know it is not the full truth because it doesn't describe many of the things that we would wish it to be able to describe. And so, nevertheless, it has allowed us to trace in much more detail the evolution of a universe from quite early moments, something like a 10th to 100th of a nanosecond, a billionth of a second. So we can go back to that point. So that's the point just before the electroweak phase transition, the temperature at which W and Z's acquire mass, and which we've been studying in quite great detail. So in the LHC, in the work that we've done in the last 10 years, we found the Higgs boson. We now have to study it in great detail. We haven't been able to find any evidence beyond the standard model, although we expected it from some elegant theoretical conjectures, which nature obviously has chosen not to chosen to ignore them in a sense. It must have other solutions which we've got to find. And so the program of work is that we will start taking data again in next year, in fact, because we're in the middle of a shutdown, and the COVID hasn't helped. It's pushed start from this year to next year. We run for 3 years, and then we stop to improve our detectors, and we start again in 2027. So that's for the next 2 decades. I think the work is very clear for us what we have to do, and it's essentially all essentially funded, and the construction is going on. But there are many open questions, and I think there just now to go back a bit philosophically to the beginning of last century. I think it was Lord Kelvin who said, all that was left was to make more precise measurements. And then came the revolutions, which are quantum mechanics and relativity, which upended physics. So I think some of the questions, because there were a few questions which were not actually properly understood, or the physics at that time did not address them. So I think there are lots of questions, some of them I've given you some feeling for, which are just as profound. And I think further progress requires the new accelerators, but also long-term planning. Now, to give you an idea, the LHC itself, which I'm still working on, first was muted in the late 70s, early 80s. That's 40 years ago. And it's going to continue for another 20 years. So it's a 60-year program. So when we talk about accelerators in 2040, 2050, we need to be thinking about them, not too far in the future. The start of the LHC was in 2010, essentially. So 30 years after it was first muted. And so 30 years from now is 2050. finally, I think that, again, this is not something which I've actually mentioned, but work we do, and it also applies to the work in other domains of fundamental science, and also David's work with the European Space Agency. They invariably lead to paradigm shifting technologies. These are not improvements of technology, they just change the paradigm, like electricity changed the paradigm, and atomic physics and quantum mechanics changed the semiconductor electronics paradigm, if you like. And also the World Wide Web has changed the communications and many other paradigms related to that technology. And these come out of the fact that we are actually pushing limits of our understanding of science, which may not seem to be, it may seem to be esoteric, but in doing these kind of pursuing these goals, we actually do produce things which are quite important. And one other thing which I could mention is Einstein probably would never have had a clue that his special theory of relativity and his general theory of relativity would be one day used in cars for GPS systems. And so let me just end by actually saying that if it's only by doing experiments that we actually reveal or confirm nature's secrets as such. So it is quite important to continue to do experiments. And it is also true that the future experimentation tends to be a lot more expensive, but a lot more people working on experiments. When I first started, we were 7 on an experiment. We are now 3,500 on CMS experiments. So the experiments, the numbers of experiments goes down as well, because the costs are higher, and not only the costs, but the people required to conduct them are more numerous, because there are different types of instruments that are required and technologies that are required, and no single person can master all of them. So I'll stop here and take questions.
Well, thank you very much, Jim. What a marvelous talk, and really, I think, making the case for this kind of activity, which is absolutely fundamental to humans, simply because we're all made of mass, and this is part of our being in this particular universe. We have a series of questions here. I will perhaps ask to take you through a few. I think the first one is from Colin Jackson, and he asks, it's a question you may have answered actually, but let's ask it. Came very early on in this afternoon's talk. Does the Higgs boson have mass? And if so, is it interacting with its own field to get this? I think you answered that question, but I think...
Yes, it does. It has a high mass, yes.
Yes. And how does it interact with its own field to get its mass?
Yeah, of course, one would argue that it starts off as massless, and then the Higgs field gets switched on, and then it acquires the mass it acquires by that interaction. So part of these become tautological answers, and in the end, I think it's fair to say that when we say the Higgs boson tells us solves the question of the origin of mass, it solves it in some manner, but it doesn't tell us why there are different particles with different masses. And I think the hope is that if you get to unified theory, then all of the masses will come out from first principle, including the Higgs boson mass, because the theory does not predict the Higgs boson mass. What it predicts very precisely is that for a given mass, how it should decay, but it doesn't tell you anything about its mass.
Okay.
So I'm afraid I have to duck that question.
That's all right. It was, no, I thought that was a very clear answer, actually. From Karwi, I'm not sure how to pronounce that. Just wondering, what if new particles do not interact via the 3 forces described by the standard model, but through an unknown force? How would we probe their existence? Perhaps you should say, how would we know of their existence?
Yeah, and I think this is an interesting question, because sometimes we think that the normal particles communicate with another mirror universe through gravity. In fact, the final thing that is left with us is gravity, and they don't interact necessarily through the normal interactions. And gravity, being very weak, then could act as a, so these mirror universes or mirror, you tunnel through these things and interact. Sometimes are put forward because we are not finding any clues respect to supersymmetry or dark matter, and people start to think about very odd ways of setting things up. So, but I think if anything has mass, it must interact through gravity. It doesn't have to interact through the other interactions. But if it doesn't have mass, doesn't have energy, then, as you said, it probably doesn't interact.
Yeah. Okay, I think you're let off at that point. Thank you. Let me move on. This is a visionary question, but what experiments of similar magnitude do you see on the horizons in the next 50 years? Well, I think you've indicated that with the FCC. Is that, but is anyone else doing anything comparable with CERN?
Not at CERN. No, I think for example, to give you a feeling for where people are actually looking at, there was a big shift, transformation between the experiments at LEP and LHC. Because to give you an idea, if we took the LEP experiment and put them at the LHC, it would have survived a few hours and died. So we've been already going at 10 years now, and we have another 5 or 6 years to go, and we're going to continue for another 15 years. So the change that would be required from going from the LHC experiments to the FCC experiments will not be as big. And so people are looking at the concepts and doing the design studies for experiments. There'll be bigger versions of, for example, the CMS experiment is, the CMS design is actually one of the core designs, because it's a fairly elegant design based on a large field, large bore solenoid, which I pointed to as one of the movies that I showed you was actually the magnet going down. So people are actually looking at, there'll be bigger versions, but not radically different versions of the experiments that we're already planning. So I think people are fairly comfortable that we will be able to build them, because when we started the LHC, it was not clear that any of these experiments could work, because we were pushing technologies to the limits, and we'd never encountered radiation problems in our work before. So we weren't sure that these experiments would even survive. And not only have they survived, they've done better than we had actually hoped for in our design studies. So that's actually something else which I wanted to perhaps bring out, that when we set our minds to doing things, we are able to do quite sophisticated things, which perhaps at first sight seem not possible.
Now a philosophical question, since I think I know your answer, but are you confident on the existence of the Big Bang? I mean, that seems fundamental in your perspective on the universe.
I think I alluded to the fact that I sometimes, when I talk about the Big Bang, I say it's a very plausible conjecture, and I think we can go back to the point of, for example, 10 to the minus 12 seconds, which is 10 to the minus 11, 10 to the minus 12 seconds, with our current knowledge, and the things like if experiments like the Planck satellite experiment, I think you probably know this much better than I do, David. If they see polarization in the CMB, that then probes even earlier moments. So the point really is to actually understand what's happening in the earlier moments. Now, to give the structure of the universe, we see that there is a passage in the evolution of the universe, which is the inflationary passage, which occurs at 10 to the minus 35 of a second. And that is a conjecture which solves many problems, but there has to be evidence for that, and that evidence might come in the next 20, 30 years' time. So I think an experimentalist would never say that I believe in this. I think we believe, we accept what we observe. And if the experimental proof exists, which is reproducible, that's the other thing has to be borne in mind. The evidence has to be reproducible by somebody else if they did the same thing. Otherwise, it's not consistent with the scientific method.
I think
and that's why I emphasize the experiment part quite strongly right at the end.
Well, in fact, it's I feel rather similarly about the need for experiment. We can fantasize in theory as much as you like, but ultimately people have to come along like you and check, find out whether it really works or how it works. Yes, so for me, in fact, the concern with the cosmology and the Big Bang is much more the concern about dark energy and what it is. You put up the embarrassing fact for astrophysicists that a very large fraction of our universe we don't know its nature. Anyhow, I should move on, and there's a question about the FCC and the LHC. Would the LHC be retained to feed particles into the FCC? Are they connected if the FCC were to emerge, or would the LHC be retired?
One of the schemes, the one that actually is costed, is using the LHC as an injector. Now, to give you an idea, CERN has this tradition that it never retires its accelerators. So in fact, it improves them. So the protons actually go through, in their journey to the LHC, go through the first accelerator built at CERN in the 1950s. Of course, it's been updated. Some of the instrumentation and the components have been changed. So one does, to get to the beam at the LHC, there are about 5 accelerators through which the beams have to pass. And so, and it's important that you hand over at an energy as close as possible to the final energy, because that makes the efficient use of the protons, and the beams can be narrower so that you get a higher number of collisions. So these are important facts. So CERN has this tradition of actually using its previous accelerators as feeders to the new ones, and I think this is this will be the case. Now, of course, one of the problems is that the LHC sits at 100 meters, and the FCC will be at 400 meters. So you need to actually dig a tunnel to take stuff down. So those kind of grosso modo, those type of problems. The idea is to reuse the LHC.
Okay, good. That's very clear. There's a question. The particle found in 2012 may not be the standard model Higgs. If it is not, what would it be? I think that's a question about the standard model rather than the Higgs, if you see what I mean.
Well, I think the reason I mentioned the 1% in my talk is that the Higgs boson, some people actually argue that the evidence of supersymmetry is the fact that we found the Higgs boson. I don't necessarily buy that argument, but it's a theoretician who makes that argument. But the point is that supersymmetry is a very elegant theory, which nature may have chosen to ignore it at our energies, because I think it does. It will be necessary at some energy, perhaps not at our energies, the LHC energies, in other words. But the Higgs, there are, in the supersymmetry theories, there are 5 Higgs bosons, and one of them is very close to the Higgs, the standard model Higgs boson. And in fact, it's only 1% different. And that's where the 1% comes from. It's in the context of supersymmetry theories, which have 5 Higgs bosons, and one of them looks like a standard model one. So we need to be able to actually make precision measurements to say that it is or it is not a standard model Higgs boson to a level of about 1/3% in some of the couplings, meaning the Higgs boson decaying into, let's say, BB bars or taus or photons and so on and so on. So that requires a large statistic, and that requires a lot of proton collisions to be studied. And that's what we're trying to do.
Okay, I think that probably answers one of the other questions. Do you expect to see further excitations of the Higgs field? But there's a question here which you raised dark energy, and obviously it's something I'm interested in as an astrophysicist, but is there any strategy direction towards finding this out is the question. Go ahead.
I think you can also probably answer that, because there are lots of astrophysics experiments, the dark energy surveys are going to be looking for and study in more detail what the nature of dark energy would be, because it's true that, is it really there? Are conjectures that it is something which is a sort of a field which then would have some particulate origin? Are these the correct hypotheses, or is something else going on? Some distortion. In fact, there are people at Imperial who in theory group who might think that actually you need to modify gravity a little bit. So I think the jury is out now.
The speed of light, for that matter. But
yeah. So I think maybe David, you can also say something about from the and there are experiments, space experiments as well, which are going to be looking at these kind of issues. I know LISA is, for example, for gravitational waves, which may have some.
We have Euclid, European spacecraft launched quite soon, actually, for looking for explanations of dark energy. But anyhow, the short answer is wait and see. This field is still, let's say, got its open aspects and waiting for experiment to answer them. Okay, I'll give you a couple more questions, and I think we really are beginning to run out of time. But any comments on possible relations between the Higgs field and the gravitational wave background? Another one taking us back to.
I think the only relation, in a sense, is that in the CMB, you actually can work out that plot that I showed, which actually shows the parameters, the mass density versus the energy density. It has a component of CMB, which then tells you that because the points sit on a line, and that line shows that the overall density is very close to the critical density, and for that 70% of the energy density of the universe has to be dark energy. So that's a second piece of evidence that comes from CMB measurements. Now, the only connection is that the dark energy seems to be have an impact like negative pressure or anti-gravity, and that is something which is a characteristic of a fundamental scalar field like the Higgs boson, the Higgs field, or the normally when I was a student, I used to call it the Higgs-Kibble mechanism, a Higgs-Kibble field, but now we're supposed to be calling in Brout-Englert Higgs field. But anyway, so there is a connection through the fact that the Higgs field, which is a scalar field, acts as if it was a negative pressure or anti-gravity, which is what's needed to accelerate the expansion of the universe.
Well,
which then is deduced from CMB.
as a space person, I'd be very happy with anti-gravity as long as I could control it. But so, in fact, a question that from John Belling: could there be theoretically a Higgs field analog to the electromagnetic field shielding provided by a Faraday cage, which is again this idea of
my unconsidered answer is no, because it has it is something which is everywhere, and because it is part of, it's the structure of the vacuum. In fact, the Higgs field actually is a vacuum field. So the vacuum is, as we have known for some time, is not empty space. It is filled with junk, which comes into existence and out of existence all the time. And so I would think that it's not possible to shield it.
Okay.
If you were to now let me stop there because I'm speculating.
Well, that was that was really fun to hear you speculate. I think probably I need to wrap it now because of the time. I think I've got a couple of announcements to make before we finish. One is to remind everybody that our next session is on the 25th of March, on Thursday, 25th of March, into the jungle volcano at 7 p.m., a regular meeting, again by Zoom, and please register. Then I must add the commercial break that we're working on next year's program. To realize next year's program, we will need some support, so please pay attention to the donations button on the webpage of the Friends of Imperial College. And let me thank the number of people who've contributed already. We're really, really good that people are contributing, but please keep up that work. I think then, finally, I've got to say thank you to you, Jim. I was absolutely riveted by the talk. It was very clear to me, but I think very clear to people with less knowledge of physics than me. It was a masterclass in presentation. Moreover, I think your perception that this is something fundamental to humanity, I think you've made that case as well. So
thank you, and thank you everybody for.
I would ask everybody to, if they can be unmuted, to show.
Thank you very much.
Brilliant.
Thank you. Very good.
Hello, Jim.
Okay, I'll see everybody next time. Thank you very much indeed.
Bye.
Goodbye.
Bye.
Thank you.
Bye-bye.
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 Goodbye.
Goodbye, Bill.